Data Communications and Network 1 class today. I'm Usana Tantulawes from Constellation University. I will talk about the constellation diagram. Constellation diagram is the word about when you look at the stars, okay, and they have the stars, constellations, something like that. But we use this, okay, in the digital communications, okay, to represent a signal, okay, as a point in the vector space. And this point is like the star in the sky, okay. So we will represent signals in the vector space by using the idea of the phasor diagram, okay. So the signal can be indicated in terms of the amplitude and the phase, like this. Okay, this is the signal, okay, in our diagram, in our vector space here, which is 2 dimensions. And you have amplitude here, which is the distance between the origin, okay, to your point, and the phase start from 0, okay, to your point. So if I have this point here and this point here, this is the amplitude, okay, and this is the phase. So phase 1, and this is the amplitude 2, okay, and the phase 2 here, okay. So this is phase 2. So they have different, the different point in the diagram has different amplitude or different phase, okay. Now, this is good for comparing various digital modulations, and especially the one with the numeric symbols, which is like MPSK or QAM, okay. And it is easy to detect, to understand how to detect the signals from the received signals correctly. Anyway, the details on the mathematics, okay, on how to do the detection, optimum detection, in the constellation diagram, how to plot it correctly with the correct unit, okay. In the constellation diagram, it will be already been explained in the digital communication class. So this one we will not repeat it, okay. So I will just go into to give you the notion, the idea of how we use this constellation, okay, to understand the digital modulation more, okay. Now let's look at the examples, okay, of the constellation diagram that we have probably seen frequently, okay. The first one is binary ASK. This is bit 0 and bit 1, okay. Binary ASK that we have seen is the OOK case, which is like not sending anything and then sending signal, right? Like this, okay. This is OOK that we have seen in the last clip. Bit 0 is like send nothing, okay. And the energy equal to 0, okay. No energy, right? Because you send nothing. And this one you send something, right? Send waveform. Okay, so you have some energy. This is only one dimension because you basically have one signal. Okay. Now, and another case is binary FSK. Actually, bit 0 is here and bit 1 is here. The 0 here is like the origin. Okay. In this case, you have the same amplitude. Okay, same amplitude here. Same amplitude here. Okay, for the x-axis and the y-axis, okay. But you have different phase, okay. For one, you may have phase 0. For 0, you may have phase pi over 2, okay. Pi over 2, or vice versa, okay. 0, you may have phase 0. 1, you may have phase pi over 2. But in terms of FSK, we don't actually look at it as the phase, okay. In 2 dimensions, it looks like they have 2 different phases. But if you have like numeric FSK, for example, 4 FSK, you have to have 4 dimensions, which means that you have 4 axes, okay, that are orthogonal to each other, and then you will have a point, okay, on its x-axis, okay, to represent the signals. The 4 signals, you have 4 points on the axis, on the 4 axes, okay. And I cannot draw that here, okay, but in the 2 dimension we can draw, okay. So the signals are orthogonal to each other, okay. So this is the 2-dimension or binary FSK. Okay, for FSK, this is 3, right? But they have to have another dimension coming out that have another point, okay, out of the paper. So I cannot draw that. Okay, now let's look at the PSK. For binary PSK, this one also use the 1 dimension, okay? So you have 0 and 1. 0 has the same amplitude as 1. This 0 has the same amplitude as with 1, but it has 0 phase, and this has phase of pi. 1 has phase of pi. Okay, so that is binary PSK. For QPSK or 4PSK, you have 2 dimension now. 2 dimension, and you have 4 point here, and the phase would be like pi over 4, okay? And then 3 pi over 4, 5 pi over 4, and 7 pi over 4, okay? Like this. For the 8PSK, 8PSK, you represent 3 bit per symbols, okay? So you can have calculate, okay, from log base 2 of 8 level, so it's 3 bit per symbols. Okay, and 4PSK is 2 bit per symbol. You can see that the circle here, you have to divide the phase into 8 phase. Okay, so this is the first point, second point, okay, third point. So you have the phase like this. Okay. This is QAM examples. Okay. For this case, we have 3 amplitude and 12 phases. So basically, this is 1 amplitude, okay, 2 amplitude, and then 3 amplitude, and then you have 12 phase. Okay, you can count that. This is 4 amplitude, okay, 4 amplitude here. So 1, 2, 3. Sorry. 1, 2, 3, 4. I think 4 is over here. 3 is here, and then 4 is here. Is the outer one. Okay. So we have point, okay, on the 4 amplitude, and then 8 phases. This is 2 amplitude. It's easy to see 2 circle, okay, and 8 phases. So they are all 16 QAM, okay, but different constellation diagram, okay. The constellation diagram usually we decide to be symmetry, as symmetry as possible, and also easy to calculate, okay. We want them to be symmetry because the symmetry pattern usually gives you the most distance apart from other points, okay, and it gives you easy to to calculate in practice. Okay, now you go to the QAM. Okay, I have skipped the QAM before because it's in the 2 dimensions and it's kind of difficult to write, okay, without showing you the vector space or the constellation diagram. So now we have learned about constellation diagram already. So I will go over to the QAM. QAM, as you have known, okay, is change the amplitude and the phase of the carrier signal, okay. Now why we use QAM? Let's look at the MPSK first. MPSK is limited by the ability to distinguish small differences in phase. This is when M is going up, okay. If you have 16 PSK, you have to divide the phase into 16 points. But if you have like 256 PSK, for example, to represent 8 bit per symbol, it's very difficult because 256, points in one circle. So you have, the degree is like 1 point something degree, okay, difference, okay. So if you have something, receive something here, and you have to know, okay, whether it's this or this, okay, it's difficult to decide, okay. Anyway, the detection is in digital communication, so I will not get into that now. Okay, but if you just think of it, if you have like many points here, okay, it's very difficult to distinguish which one it is. So if you can increase the amplitude, okay, like this is 60 QAM, and you have 3 amplitudes, okay, and then it can help you, okay, to distinguish which is which, okay, it will be further apart. Okay, so this is good. Okay, so we should usually for non-binary cases, if you have, high M, we always use QAM and not the PSK. Constellation diagrams with us the time domain signals. Okay, this is the QAM. Okay, 1 amplitude. This is actually the same as QPSK or 4PSK. Okay, because it has only 1 amplitude, so it's basically the same. Okay, so it has the same length, okay, of the amplitude, the distance, the same distance from the origin. This is the 8 QAM, which is 2 amplitudes, okay, and 4 phases. This one is good in terms of that it use the gray code. Okay, I mean this one they use gray code. I have talked about gray code before, right? Okay. Now for the second one, I will map it to the time domain signals. Okay, so that you can see what it is. This is actually 2 circles here, 2 amplitude here. So I will use A1 psi omega ct plus theta and A2 psi omega ct plus theta. Okay, so let's say that this is a small amplitude, this is the big amplitude. Okay, the small is like the shorter distance from the origin. Okay, now let's look at 101. 101 is here. This is the big amplitude, okay, large amplitude. So this is basically A2, right? Psi omega ct plus what? The phase is pi, plus pi. Then you can draw this signal, okay? This is for this range, okay? For this timing of 101. Okay, psi is like this. If you don't remember, this is psi. Okay. Okay, so this is 101. Now, what is 100? 100 is this. It's the same shape as 101, but with the smaller amplitude. Same shape, but smaller amplitude. Start with pi, phase pi. Okay, so chip, this is pi. Smaller amplitude. Okay. So this is the waveform. Okay, and 001. 001 is what? Is this one. Okay, 001 is high amplitude and phase 0. Okay, 000 is low amplitude and phase 0. 010 is low amplitude. Okay, low amplitude and phase pi over 2. Pi over 2 is this. This is phase pi over 2. Okay, and 011 is the big amplitude and phase pi over 2. Okay, so you can do this to finish this by yourself and also try it yourself. Okay, use the basis, okay, to be change the basis, okay, to A cosine omega ct plus theta A1 A2. It will be a different waveform. Okay, instead of using the x-axis here as a sine, use x-axis as a cosine. Okay, and then draw this waveform again. Okay, to see what happened, because cosine is different, right? Cosine start at here. This is cosine omega ct. Okay, so try this. If you have problems, then you can ask me in class. Now let's look at the bandwidth. Okay, baseband signal that center at the 0 Hz. Okay, without the modulation, the low frequency signals. Okay, without any carrier. It have the minimum. Okay, let me tell you the minimum bandwidth for the baseband is D over 2, where D is the baud rate. Baud rate is symbols per second or pulse per second. Pulse per second. Okay, so example, you have D equal to 1 megapulse per second. Okay, and then what is the minimum bandwidth that you can send for baseband? Okay, is D over 2, so 0.5 megahertz that you need, okay, to send this. But this is in theory. Okay, usually you cannot do that. You have to, in practice, okay, you have to increase a little bit more. to make it a more practical, bandwidth, okay, to have a more practical shape to use. So it's going to be 1 plus r multiply d over 2 and 1 plus, and r is between 0 and not more than 1, okay, usually. So suppose r is 0.1, okay, so transmitted bandwidth for baseband, okay, would be 1.1 times 1 megapulse over 2, okay, so 0.55 megahertz, okay, is needed. Now, this is the baseband signal, center at 0, okay, this is the bandwidth B. When you modulate it, it will center at FC, right? And this is the bandwidth, okay, so total is 2B. This is the modulation, simple modulation, that is called double sideband transmission, okay, this is simple modulation. You usually study this in principle of communications class, okay. Anyway, so this is like FC plus B, this is FC minus B hertz, okay, so the total bandwidth is 2B. You basically, you increase the bandwidth, double the bandwidth, right? Okay, so if you modulate the signal that use double sideband transmission, okay, you modulate it with carrier, then the minimum, okay, whatever you have for the baseband, you have to double it for the modulated signal. So B min would be d hertz or 1 megahertz, okay, become 1 megahertz, and the practical will be 1.1 megahertz, okay, for our examples here, okay. And this is very important, okay, this one very important. I summarized for you, okay. ASK, PSK, QEM use the same bandwidth formula, 1 plus R multiplied by D. D is the baud rate, okay, symbol per second or pulse per second, and basically is this one, okay. So I just make it clear to you that this is important, how to calculate the bandwidth. Now let's look at the bandwidth of MFSK or non-binary case, okay, which k bit per symbols. For example, 2 bits per symbol, so you have 4 frequencies, okay, for FSK. In this case, okay, look at it, look at the picture here. So you have minimum frequency and the maximum frequency, okay. If it's 8 FSK, then you have 8 frequencies here, right? So what is the bandwidth? The bandwidth is from F min to F max, right? But in practice, okay, we cannot send only that, okay? You cannot have like the carrier at the boundary of the bandwidth, okay? So we will approximate, okay, by adding 1 plus T on the left and on the right, okay, as the tail of the bandwidth, okay? So we will actually use this one as the bandwidth of FSK. Okay. Now, what is why I add 1 over T? T is the symbol's duration, okay? So you basically you can send if you T is small, so you send a lot, okay, of symbols in 1 second, in a second. So, okay. So if T is larger, you send fewer symbols, okay? You send fewer symbols in a second, okay? So this is basically high pulse rate. So if you have high pulse rate, okay, high pulse rate, okay, I will have more of the 1 over T, right? So T is small, 1 over T is bigger. So if you send fast, okay, I will, have more bandwidth at the tail, okay, to accommodate that. So this is approximate. Now the bandwidth, okay, basically F max minus F min, okay, plus 2 over T. So basically directly from the picture, you got this. And if you don't have Fmax and Fmin, but you do have like how many frequency it is and the difference, okay, delta, the difference, frequency difference between each adjacent frequency. So suppose k equal to 3, so you have 8 frequencies here. Suppose you have 8 frequencies here. So the difference here, you have 7 difference, right? So 8 minus 1. That's why 2 to the k minus 1, okay? Because you add 8 difference, and the difference will be delta. The difference of the adjacent frequency will be equal, okay? So, and they will have some, some formula, some way to calculate to make them orthogonal. Usually we use it as orthogonal, modulation. So FSK, we have some specific values, okay, that we want as a delta. So we have delta here multiplied by 2 to the k minus 1 and then plus the tail, okay? So this is the formula for the FSK. Now let's look at the performance comparison of what we have learned so far, okay? So I have the PSK, QPSK here, ASK, FSK here as a digital modulation. I also have the NRC, okay, and the biphase here, AMI and the pseudo-ternary here. So this is also the line coding topic, okay. This is the bit error rate, probability of bit error rate, okay. And this is EBO and 0 is like signal to noise ratio in bit, okay, or per bit, okay. You can see that this one is better than this group. This one is worse in terms of what? Okay, let's look at this. If you want to have the same probability of error 10 to the minus 5, okay, for the better group here, PSK, you will need about 9.5 dB of signal to noise ratio. But for the worst group here, like ASK or FSK, you would need about 12.5, okay, to have the same bit error rate, okay. So you need more higher signal to noise ratio, and the noise is the same. Basically, you cannot do anything with the noise, so you have to increase the transmitting power, okay, transmitting signal power, okay. So you have to pay for it to get the same bit error rate. But if you have the same EBO and 0, okay, you can see that the bit error rate, okay, of the better group here will be 10 to the minus 5, but this one will be 10 to the minus 3, okay. So it will be better in terms of the bit error rate. I also have the proof, which I didn't put it here. I have to save time, okay. So the proof is in my lecture notes, okay, the detailed lecture notes. Anyway, the relationship between the data rate and the bit error rate, okay, that you should know. If the data rate increases, then the signal to noise ratio in bit, okay, will decrease, okay. Again, the proof is not in here, in the lecture notes. So if you are in my class, you can read that. And the bit error rate, okay, will also increases, okay. So basically, if R increase, bit error rate will increase, okay, unless you increase the power, okay. So if R increase, bit error rate increase, okay, if the signal power remain the same, okay, the same as this. If you want to use the same signal power, okay, so SNR remain the same, then you have this point and this point, right? So if the bit error rate increase, you will get okay, 10 to the minus 3 and 10 to the minus 5. This is the bit error rate, okay. So look at the picture, look at the graph, and look at this. And also, we can take a look at the okay, relationship between the EBO and 0 and the bit error rate. It will be more direct, okay. Basically, I have graph like this, This is over n. Suppose at first I have this one is EB over N0, 1, okay? I decrease it into EB over N0, 2, right? And then this is the first bit. This is my first bit error rate. Bit error rate 1. This is my second bit error rate 2. So you see that when I decrease the EB over N0 from 1 to 2, my bit error rate will go up. Okay, this is what shown in this sentence. Okay, so this is the end of the clip. Okay.